So that's apparently how you share your screen on an iPad. You have to broadcast it. But we figured it out. And thank you everyone for mentioning all your really cool things you've learned the past week. I wish I'd have more time to go through things, but since we're already running late, I'm going to just try to race through. And let me that. Okay, so again, we've already done the Canvas thing. I have the attendance quiz on the bottom right corner of every slide if you can't find it. And we'll do our pre-lab Zoom feedback now, I guess. Kim, if you wouldn't mind starting that. And then while we're going through that, I want to note that Piazza has not been as widely used as it previously was, but it has a lot of good resources. I have answered some questions. I don't know if they were useful answers because I kind of went off into space about quantum physics. People ask a lot more about like research and kind of more advanced topics. So I'd highly recommend using Piazza if you are interested in getting some more background on certain topics or have questions about the homework. That's definitely the best way to go about that. We've done our attendance quiz. Again, I have the code in the corner. It's this over here. And we are lab number 3. And we're interested in, I guess a lot of you have probably already taken it, but it is how many hours you spent on last week's homework. We're interested to hear if it's too much or too little, whatever is going on. Okay, great. So today we're going to be talking about probability and random variables and kind of different functions for probability, what the probability of 2 events happening is, and how this all relates to quantum information, how this relates to your state vectors, and what that all means when we're talking about quantum computers. So this last little bullet here is hopefully going to be the really fun stuff if any of you have been waiting for more quantum topics. So questions from last week when I go over, and I'll also open up the chat for any more questions you guys have. But the way that we've been told to discuss complex numbers from this point forward is just pretend like it's a scalar. It's not strictly true. You do have your complex plane. But if you are ever confused about if, for example, you want to represent a number like this, and there's your vector, maybe this is like the state that you have, you can maybe separate it out if that would make you more comfortable with it, and just put the I outside. And so a lot of times this I, and when we represent this in the block sphere, the I is e to the I pi over 2, or that might be a negative I. One of those, that's plus or minus a minus sign. That is your phase factor, and then that can just easily be pulled out of the term. So for our purposes, we'll just treat these as scalars. You don't need to represent these as little like vectors within your vector. I know I showed it like that last week. I forget if it was in this section or a different section when asked, and that is an accurate representation. There's a lot of equivalent representations of the same information, and for the purposes of this, we're just going to treat them roughly as scalars. Obviously, they do have special rules when you multiply them, but as long as you treat this I as just kind of a square root of -1, any kind of multiplication will still work through that way. Okay, and then the next question was why we take the transpose of one vector for the inner product. And this is just for the purposes of being consistent with the way that we do notation for higher dimensional objects like matrices. So the thing that, if I have it written out here, I have it written out, so I'm not going to write it out. Here, I try to make slides and I want to scribble on the first slide and not go to the rest of them, and then I just skip the rest of them. But so it goes. So whenever we have a vector, we always want to have the second number, or the number of rows or number of columns match the first number or the number of rows with the second vector. And this is because this is how you multiply any kind of matrix. So if instead you had you had two 3x4 vectors or 3x4 matrices, these don't match. These are not equivalent. So you would need to take the transpose of this one to multiply the two, because when you take the transpose, you functionally invert the two values. So this transpose is 4x3. And then that can be multiplied by the 3x4 from before, because these two match. And that's just how we do matrix multiplication. I have this written out for this example. So we just always need the inner dimensions to match. There's nothing super special about it. It's just how this multiplication is defined. And so we do this for vectors as well, just to be consistent. And here's another one. So this is just noting that what I said before, like that we just want to make sure we always have this consistent rule. We're not using different rules in different situations. So with that, I want to open it up if anyone else has questions about the content we covered last week, which again was mostly on this matrix multiplication. And there will be more opportunities to ask questions as we proceed. Okay. There aren't any immediate questions, and I didn't leave it very long, but just since we're a little behind due to my fault, I'll just move on. So the topic of the day is probability. Why are we interested in probability? Well, it was covered in lecture for you guys, but the big picture is just that quantum mechanics is probabilistic. This was originally seen with the double slit experiment, or I guess not the double slit experiment, but a bit. You're seeing the interference of two quantum particles, and you can tell that you can note that the actual result on like a single particle level does not give you this whole quantum mechanical wave function. You can't back it out. But when you take a bunch of different points, you can back this out because you're functionally measuring the probability of the particles. So whenever we're doing a measurement for a quantum mechanical particle, we are measuring the probability of what state it's in. We're not measuring, and when we have it in a well-defined state, where, for example, we want to have it in like the 0 state. So we want to have it like this. This just means that if we measured this, we have the probability, I guess I'm right, as P is equal to 1 for that state. And that's kind of what we're measuring all the time. We're doing measurements of quantum mechanical systems. So now with that justification, I want to discuss probability that you guys have seen before. So if people could put in the chat examples of probability they've seen in their daily lives. I'm sure many games, for example, use probability. There's other examples that you guys can think of, but if anyone can think of an example, this, and thank you, Naveed, for loot boxes. Yeah, that's a very common one, I guess, now. Coins, yeah, flipping a coin in Qubit Cruise. Lottery, yeah, the lottery is a probabilistic system. You, Jason. The weather forecast, that's really interesting. Thank you. Yeah, so like if you have a 50% chance of rain. So I'm gonna make sure to note this because we have everything noted as a number from 0 to 1, but the idea of 0 to 1 as like a range, or I guess I'll note our range. I guess I forget if this is inclusive or exclusive, but this can also be represented as 0% to 100%. All you've done is multiplied by 100 and added this percent sign. So if you're ever confused, and I'll go into this, I'll give examples of this later on. Yeah, thank you, Elon, for drawing cards. Thank you, everyone, for all your suggestions. Yeah, just your the probability of just anything happening in your life. We're all very complex systems, and I guess we're made of quantum mechanical particles. So technically, like we have all that probability kind of from the ground up. But I guess if you're interested as to why we don't just like spontaneously tunnel through walls or anything, it's because we're such large, massive particles that can't happen, or we're such large, massive things that can't happen, because the probability of that happening is proportional to like how large you are. And then also, if you're wondering why nothing is random, like on us, it's like really visible, is because we have so many particles that make us up that they all average out to just a stable state. So you don't see these effects because of the combination of the large number of particles and just like the large mass in total. So yeah, thank you all for the suggestions. So now we're gonna discuss the probability for a six-sided die, which I know a few of you mentioned. We know that if we have a fair dice, then we have an equal probability for every single one of these outcomes to happen. And how do we represent that? Well, we know that we must have all the probabilities be non-negative. That is a requirement for a probability. That's not actually a requirement for a probability amplitude, which is what we deal with in quantum mechanics. So if you're ever confused as to why you've gotten a negative number out, the probability amplitude, or I guess the prefactor you get on your quantum state, we'll go into this a little bit more, is the square root of the probability. Or a lot of times it's not quite the square root, I guess it's the dot product of its transpose times itself, or it's of its conjugate transpose times itself. And so we end up with numerically, like in a scalar form, just the square root of that value. Yeah, sorry for going like all over the place with this. But yeah, our probabilities, not our probability amplitudes, must be non-negative, and then all the probabilities must sum to 1. And again, this is the same constraint that, because we want to get to 100%, and 100% is equal to 1. The conversion factor, I guess, is you just multiply by a percent sign and divide by 100 to get between the two. If that makes it any more, I'm sure you guys dealt with percent signs, or I guess we divide by 100 and a percent sign, actually. That's, yeah, there we are. So yeah, so the probability for a six-sided dice, we know that all of these probabilities must be equal. So we can take each of these probabilities to be P. So we say the probability of this is P, the probability of this is P, all the way down. And so we want to sum up these P's to be equal to 1. And we know that these P's all together, I'm gonna say that I don't like how this is written out, and I'm gonna write this as 6P is equal to 1. And then you just invert that equation to get this final answer, that the probability of each outcome is 1/6. And if you would rather note that as a percent, I guess, what is 1/6 in decimal? 1.67. So this is equal to or 0.167 in decimal. And so that could also be represented as 16.7%. So you have a 16.7% chance that you get any of these. And these are all completely equivalent representations. These are all the same number, just represented different ways. Okay, so we have that. Now, if instead we want to describe the probability of a certain outcome, if we know that the outcome is 5, what is the probability of that event? So our event is that the outcome is 5. And so this is like our probability symbol. I guess it just means that we're taking the probability of some variable. We often call them random variables, but I guess they are a variable. It's the probability that something has happened. Something in particular has happened. So we can look at this kind of, I guess, outcome probability table the same way we look at a truth table where you just read it through. Can anyone read off what the probability of event A, where the outcome is equal to 5, is? It should be pretty simple, but I promise you it'll get much more complicated very soon. Thank you to Jenny and Tomas and Dristi and Carlos and Adim Chima and Megana. Yes, you're all right. We just want to look at this row here where the probability or the outcome is 5 and our probability is then 1/6. Now for event B, the outcome is more than 1 and less than 5. So that does not include 1 and it does not include 5 in here. So it's just, this is a non-inclusive set. Yes, thank you everyone for sending yours. Yes, thank you Dhruv and Dennis, and Megana, and Elon and Maxwell, and Xavier. So yes, what you want to do is you want to add the probabilities of each of these outcomes. So I'll write them in maybe a bit of a confusing way. So we're looking at the probability that we are more than 1 or less than 5, which is that region. So we want the probability that our outcome equals 2 plus the probability that our outcome equals 3 plus the probability that our outcome equals 4. And so that is 1/6 plus 1/6 plus 1/6, or 1/2. And that's how you work through the probability of one of many outcomes being the results. So now we're going to get into something a little bit, I guess these are kind of similar examples. And I guess I want to try something different today. If anyone is interested, I've heard from other TAs that they let some of their students unmute and go through things. So if anyone is confident in their ability to explain how you get the probability for event C happening, which is where the outcome is an odd number less than 5. So you're in the space less than 5, which is here, and your outcome is odd. If anyone would be interested, I guess just raise your hand and I'll see if I can figure out how to do this reasonably. Okay, great. I've gotten a request from James Tang, if you'd like to unmute and explain how you think how event C would happen or what the probability of it is. And I can call on someone else. Oh, is unmute not available? Let me see if I can unmute you.
People should be able to unmute themselves.
I can ask to unmute. Okay, you should be able to.
Okay, can you hear me?
Yep.
Okay,
great.
So all numbers less than 5 is 1 and 3. So we add the probability of 1 and the probability of 3 together, and you get 2/6, which simplifies to 1/3.
Great, thank you so much. That's exactly right. Yeah, so you have probability of 1 plus probability of 3 is 1/6 plus 1/6, which is 1/3. So that's it written out. Okay, it's not a terrible idea. Everyone's wonderful. James, thank you so much for giving your explanation. I think it's good to have people that maybe are seeing this more close the first time explain it, because I've been dealing with probabilities for 10 years, so it's all terrible. I understand things. I've dealt with these things for too long, and so I'll start explaining something and you guys feel like, well, I have no clue what you're talking about. And it's just like, oh, well, this is just a fact of life. It's like saying the sky is blue, but that's not true. If your skies never existed before, then it doesn't make any sense to you. Okay, so now for event D, I've gotten some raised hands from Thomas. Meryl or Beryl, if you'd like to give your explanation for event D. Let me see if I can prompt.
Okay, can you hear me?
Right. Mm-hmm.
Okay, so it's even numbers that aren't 2. So
yeah,
the only even numbers that aren't 2 in the outcomes are 4 and 6.
Mm-hmm.
So you would add the probability of 4 and the probability of 6 together, which you get 1/3. And that's it.
Mm-hmm. Nice, thank you so much. Yeah, so that's exactly it. So I guess this kind of union and intersection that we've noted down here is another way of explaining the same thing. So this is how we just, how Thomas so kindly just explained it, where it's kind of the same result as we always have. But if instead you want to look at the probability, this is I guess this isn't the union of the two. If you have the probability of 1 being the case, and what you want the probability of where S is the case, but T is not the case, you want to remove, I guess, we want the probability of S even union of 2, but we don't want we want to remove duplicates of this. So we take the probability that it's even. And this is not, I guess, quite the same thing, because we want where it's not 2, I guess, here. So the likelihood that we have an even number is 1/2, but we can just write this as even, plus the likelihood that we are not 2, which I've just done like this bang. I can write that non-programmer notation to make it more clear. So we have 5 out of these 6 are not 2, but then we also want to remove the terms that are, I guess, present in both of these. So if we are even and we are not 2, let me see if I can get this written out correctly. I guess that's just this like is the intersection, I believe, of the 2. And you just remove that overlap so you don't end up with both of them counted. So I guess, I don't know how it's easiest to write this, but we can just write it as P even. Yeah. I'm not going to go into too much more detail on that. We'll see this notation show up a few more times, but all that means is just removing the overlap. We don't need to go through that, I guess, again. Yeah, okay. So now we're going to discuss this more in the form of random variables. So when we have a random variable, we take the probability of a random variable. We will get a number for whatever that random variable, or whatever the likelihood that random variable occurred in that way. So you could have a function for this random variable, and that would give you outwards the probability. So this, and the way that we've described it before, if we're taking this probability of X, and so for here, we want to take the probability of 4 for a particular role, which we discussed on the previous page. is 1/6 if it's a fair dice, and etc. For the same thing goes for the rest of these. The probability, like again, we have the probability of 2. I guess we don't have a function, I guess, explicitly for what the probability of x is. But in our case, since we know the probability of any of these variables is 1/6, we can just say that the probability of x is actually 1/6. So the function of this variable, we'll go into the next page, but I just want to draw it out just because I find it more intuitive when it's worked through. The probability of x is just a line at 1/6. And this can be, I guess our set is 1, 2, 3, 4, 5, 6. And technically, this isn't defined at any points but these discrete points, because a dice is a discrete value. So the specific way for a discrete probability, we'd put a point, I guess, here at each of these. But you can look at, I guess, the envelope of the shape, and you can see that it's just a line across it. We can also describe probabilities for continuous variables rather than just discrete variables. But that's a little less intuitive, and we won't have to deal with that right now, I guess. So here is our probability function written out. So again, this is they call it the probability mass function, or the PMF. You'll see it written a lot if you look this up. I believe for continuous variables, it's the PDF, the probability density function. But for discrete variables, it is the mass function. And in this case, the probability for each of these possible x's is just 1/6. And so you can draw this out with these bars. Again, if you kind of want to look at it as an envelope, you could just draw a line across something. It's always 1/6, because our function is actually only defined at these discrete points. So you don't really have to think about what these values are in between, because we're not dealing with the possibility that a dice lands on its edge at all in this setting. So with that, we now want to expand this to not just the probability of something happening, of a specific event happening, but functions of these event variables, these random variables. So I want to introduce first the expectation, and then we'll deal with the variance on the next slide. So the expectation of x is often described with these I guess angle brackets. We do have this is not the same thing as when we have these bras and these kets. This is an expectation value. So don't confuse them with like the bra, like this. So I guess bra ket. Don't confuse them with that. It's not the same thing. And the way that we define this is the value of our random variable. So this is the value or the outcome times the probability. And so this is the written out version here. But what that means is the value that we get out of our expectation value is if you rolled the dice 1,000 times, the average value you would get would be 3.5, because we would functionally have taken a bunch of random samples that would all have this probability. And then we are, we're summing over each of these normalized the probabilities. So I guess when you take an average, because this is a very closely related idea to an average, you take, I guess, the sum of the values you get over the number of times you did something. So this is guess I'll try to keep the notation consistent. We do sum over n, where n is the number of times you threw it. Like if you threw your dice. This is our average value, is the sum over all the values that you got out, these n times, divided by the number of times you threw it. And so you can, instead of having this, I guess this number of times you threw it coming in the bottom, you can instead place that as a probability, because the number of times you'll get value X, I guess this is completely equivalent to if you, for example, threw the dice. Let's make this a coin instead of a dice, just for the sake of describing it. If you threw a coin 5 times and you got heads 3 times and tails 3 times, we'd have 3 times heads, which we'll describe as 0, plus 3 times 1, which will be our tails, and that's divided by 6. And so this is the same as having 1/2 probability that you got the 0 plus 1/2 probability you got the 1. And that's exactly what we're doing with this expectation. We are generalizing the concept of the average value you got when you did something many, many times. And of course, for a dice, if we set this to 0, then this will just end up with 1/2. Our average value would be 1/2 if we have a 50% probability of getting a 0 and a 50% probability of getting a 1, which I guess that's a very straightforward number to get out. But it's quite a bit more confusing when now we have a bunch of numbers from 1 to 6 that we're summing over. And so the average value of when we throw a dice 1,000 times, is the average value we're getting is 3.5, which I guess makes sense because we are between 3 and 4. Like that's like the median value of our set, and we have an equal probability of each value. So hopefully that makes sense. So now we're going to go on to the concept of variance, which is trying to describe how much we deviate from our average or expected value. So again, this is the same function as we had before, and then we're additionally taking the expectation of this entire formula over here. And so you can instead treat this as summing, or we're now like, we can instead treat this as the, I guess, written out version of this expectation. So this is now our, or I guess this whole thing is now our value. And this is our probability. And we're doing the same format. And this variance doesn't necessarily need to be, like it doesn't have to be within the set of values you can actually achieve. So obviously if our average value is 3.5 and we added 2.92 to 3.5, we're now getting, I guess, 6.42, which is greater than 6. That's completely fine. You can't actually get that value out. Actually, did I do this right? It should be, yeah, that's right. Okay. Yeah. So this, you can actually get a value that is, or a variance that would result in some finite probability of getting a value that's actually not possible to get. But what this is telling you is kind of what the shape of the envelope over your probabilities is. So we discussed it as kind of a straight line or a flat line before. What you can think of this is telling you, if you, I'm sure many of you have maybe seen a normal distribution before where it just looks like a bell. This is approximately, your variance. And so you can end up with something like what we showed before, where we have a bunch of discrete values, and our curve maybe looks like this. So we do still have some probability of being over here, even though there's no values that we're actually going to end up with over there. So don't worry if that doesn't feel intuitive. It works out well mathematically, and it is like just a standard way of describing what the variation of something, or what the variation of some function is. Okay, so now we're looking at the PMF, or the probability mass function, which is what we defined before, for an unfair dice. So again, that this is our probability, this is our random variable. Yeah. And we've now defined what this probability mass function is. So this is our PMF. And we defined the value for every possible random variable value except for 3 as being now only 1/10. While for 3, it's 1/2. So we're much more likely to get 3 than anything else. And so now we can do the calculation for the expectation value and the variance for this new probability mass function. So this is just the exact same calculation. I'm not going to run through it in too much detail because I am dramatically over time already, or no, like I'm going to be dramatically over time already, and I want to get through as much as possible, but I can go through this at the end if you guys want me to. But it's just doing the exact calculation we discussed before with this function, and we end up with our expectation is 3.3, which makes sense. We want it to be close-ish to 3. Because that's their most likely value. And now the variance is lower than for the fair dice. And that makes sense as well, because now if we drew out, let me just do it over here. If we drew out kind of what our envelope for what this function looks like, we would probably draw it more like this. Or I guess we want it to be still like a bell curve. What's the best way to do this? There we are. There we are. Okay, so this is smaller than if we had a curve maybe for the previous one. We took that as being like here. It's much smaller. And so that's why we expect our variance to be smaller. It makes perfect sense that we got this lower value. So everything is consistent. So here's another view of the histograms that you guys can look at while I take questions. Are there any questions about this section of the context? After this, I guess we're gonna go, I think, briefly into joint probabilities, and then we're going to go into Brockhead notation. And I guess there was a question, Rohan, that I guess you guys answered. Well, why don't you start with 0 for the dice? For a standard dice, you can't have a 0. You could redefine all your variables, but if you're looking at the actual outcome, you want whatever corresponds to your physical system. I've got a question for kind of explaining the variance again. So I guess I'll just draw it out again, because I think that's like the easiest way to think of it, is if you decided to create like some kind of continuous function. I like to think of it this way. Maybe it makes less sense, but it's how much your value varies from your average. So here, your average is right here. Your expectation of X is right here. And we want to look at how much our value varies. And we know that this is 2.92. So I guess I forget if it's actually the half of that or full of that. I don't really deal with these too often. But you want to kind of describe what how far you go from your expectation value. So here we still have quite a decent likelihood that we get 1. We don't have any likelihood we get 0 or 7 or anything, but we want to look at the spread of our values. And so if I think I'm just going to draw a function again, but if we wanted to draw this as a bell curve, we draw like a really fat one that goes like here. And so this would be a description of our variance. While over here, we would instead draw a skinny little bell curve that it should be even. And so this is our variance here. And so that's how I just think of it, is how much your outcomes will vary from your expectation value. And that will be, that can be described as a kind of a function of these histograms. It's not, I guess it's a well-defined value, but it is just defined a certain function that we expect. And then, so I've gotten questions for the formula that I showed is applicable to only cases where the outcome is a numeric value, and that is true. What you would have to do if you wanted to describe a system where something is not a numeric value, which I guess, like if you describe like heads or tails, you'd have to assign a number to heads and a number to tails, and the expectation value and the variance are maybe not very useful descriptors if your value is not, or if your variable is not numerical. However, if you want to do some kind of calculation with these variables, then maybe you'd want to convert them to a number. You want to assign heads is equal to 0, tails is equal to 1. What's my expectation? What's my variance? And then you can calculate the variance of your function. But I guess it's not, the raw number is not meaningful necessarily. I'd say you wouldn't want to take an expectation or a variance if you don't have a number system to describe this with. Because otherwise, like you're just, I could assign heads is 25 and tails is 3. Like it's all quite arbitrary. The mapping between the two is really where you're deciding what your expectation variance will be. So I guess you wouldn't do it for something that's non-numeric. But that's a very good point. Thank you to Rohan and Jenny for that question. And Joel as well. Okay, so I'm gonna move on to the next section just for the sake of time, because I wanna get through as much as we can before we run out of time for the day, because we are down to like the last 5 minutes already. Okay, so now we're going to talk about the probability of a dice and a coin. So we've now created 2 columns here, where this is our heads. That wasn't clear. I don't know why we didn't write that out. And this is our tails. And then this is still just our 1, 2, 3, 4, 5, 6 for our dice. And we know that the probability of every single one of these is equal if these are fair. That's the whole point of coins and dice, I guess, is to make them, or it's not the point of a coin. Coins are legal tender, but like when you're flipping a coin, the hope is that it's pretty fair. Maybe a few % off either way. So we want to divide these 12 probabilities. So we can treat this the same way as we have 12 probabilities. So we want 12 times p if the probability of each of these states is p. I guess I'll write this out a little more clearly. The probability of, I guess, 1 comma tails is p, etc. For all of them, we want 12p to equal to 1. Therefore, p is equal to 1/12. And so this is a pretty simple I guess, result, since these are both fair. So now we're going to take these random variables for these two. And I guess this is exactly what I did before, where our heads is 0, our tails is 1. This is all a bit, it's all a bit arbitrary, but if you're trying to compare something that is numeric, something that's not numeric, it makes sense that you want to make everything numeric. And so to get the probability of two things happening where we've done two independent events, this, what we're discussing now is fully independent events. We've rolled our dice and then we've flipped our coin, and we found, we found a bunch of times that the probability that that our coin or our dice gives us 4 is 1/6. The probability that our dice gives us 0 or heads is 1/2, and we just multiply the two when we're dealing with independent variables. That's what I really want to stress. This is independent. We could have rolled the dice 5 times to get the value we wanted, and like not really, I guess, like not really paid attention. You could roll the dice a bunch of times, flip the coin a few times, come back to the dice a bit later, and then decided we wanted to take the 5th value, or the 5th time we rolled the dice, and the 2nd time we flipped the coin. And every single time we rolled the dice, we flipped the coin, those events were independent. Every time you roll the dice, you have a 1/6 chance of getting each value. It doesn't matter if you rolled three times in a row. The 4th time you roll it, there is still a 1/6 chance you get a 3. And it's the same thing with this coin. If you've rolled the dice and you've gotten a 5, that 5 does not impact the likelihood that you get a heads on your coins. That's why we just multiply these two probabilities, is because everything is independent. So now we want to kind of try to do, I'm going to try to just do one example, I guess. Just do event A, or actually I'll do event B, because we practically just did event A. We have event B. We want the outcome of the dice to be less than 3 and the coin to give T, or tails. So we know if we take less than 3, that means that it can be 1 or 2. So probability less than 3 is equal to probability 1 plus probability 2, which is 1/6 plus 1/6, or 1/3. The probability that the coin gives tails is 1/2. So therefore, the probability that we've gotten less than 3 and tails is 1/6. And that is how you do these joint probability calculations. So now we're doing, yeah, now this is just like plotting out kind of what this looks like. And this is where we've noted this is the dice value and this is the coin value. And we've written it like this, where it's just common, like a comma between the two, because this is consistent with how IBM does this on their quantum experience website. And so we wanted to make it consistent with that. You could also do this in a grid instead, where you do a 2D plot, I guess, with these histogram bars. And I'll leave it as an exercise to the reader if you would like to represent it that way instead. Okay, so now I'd like to take questions, and we are at 8. I'm just going to keep going forever because we need to get through this bracket notation, and it's really interesting and really fun, but this will be recorded and put online. I'm sorry for being late and not knowing how an iPad works, but it will be online. So if you need to go now, no worries. It should be posted on Canvas within a day, hopefully. But I'll open it up for questions on the content discussed so far. So I've gotten a question for, if we have a hill at 2 places on the graph, what is the variance? Rohan, that's a very good point. So let me, I guess I'll just draw out my own graph. Why not? If we had a tall thing here, and then maybe some small ones, and then another tall one, and then some small ones. And this is what our histogram looked like. Well, we still define an expectation value. And if we assume that these are roughly the same, they're not quite even how I've written it. Our expectation value would still be here. And so we know that our peak needs to be there. But because we have these like really tall things, we're just going to have a very wide variance, is kind of the conclusion here, to spoil it a bit. But we just want to have, like a big wide thing, because we want to get, and it doesn't always have to go over the two. We're just going to have a wide result. So now Clark has a good question. If it's not equal, so now let's go and do the unequal version. If we took one hill is like twice the height of the other, perhaps, or not twice the height, but like substantially taller. Let's say this one goes up to here. Well, then our expectation value would move to be renormalized by the likelihood of this guy being the most likely of everywhere. So maybe it'd like sit, let's just say it sits roughly here. This is all non-numerics. This is just kind of intuitive. Don't try to back out numbers from this. This would now be our expectation. And so now I guess we'd have a bit of a narrower distribution. Yeah, we'd have our peak be like here, I guess, where it would be a bit narrower because now we don't have two equal height, equal likelihood values with a peak in the middle. But instead we have a very likely peak here and a less likely peak here. It would still be wider than if it was just this one peak. If it was just the one peak, maybe we'd get something that looks more like this, where it's just like right around there. But just the width of these distributions is going to be the variance regardless. And yeah, cool. So yeah, if the hills aren't equal, whenever you have whenever you have a distribution where one thing is the most likely, your variance will be reduced. If everything is equally likely, that'll be your widest possible variance. And so that's how you would how you're best off thinking of things. Yeah, very good questions for everyone. Okay, so now we're going to move on to Braquette notation. Hopefully we'll end before everyone needs to go to bed. So now we're discussing, this is back into the quantum realm. We have what we've shown the whole time with, oh no, I'm going to start getting a bunch of messages. With this being our ket here, which corresponds to a column vector, and then this being our bra, which corresponds to a row vector. Whenever we want to take the product of these two, we will always end up with this, with the, I guess this is, whenever we take the inner product of our full state, which might not just be a single bra or a single ket, we will always end up with 1, because everything should be normalized in our quantum space. Like everything, the probability of this entire state existing will be 1. Because we know that we have a state, it's just the different components of that state might have different probabilities. So yeah, I guess that's the easiest way to think about it. So we do have other states that aren't, I guess that are superposition states, but we can also treat them as their own basis. So we have, I'm probably going to write this wrong. We have the idea of a plus state, which I think, I don't know if it's 1, -1, but it's one of these like 1, -1 or 1, 1 type states. And so we could take the inner product of plus, and that would give us 1, -1, 1, -1. Oh, and this should be normalized actually. Let's note this is normalized by square root 2. I realized I did not have that. before. That's important for these states. And so this will give us a 1/2. And that will give us 1. So that's where you see that this normalization factor is really important, because without that, you'll end up with a resulting, I guess, probability that's higher than 1, which isn't physical. Your maximum probability is always going to be 100%. You're not going to get 2 particles for nothing. Yeah. So now I'm going to describe these qubit states as with these bras and cats. So our qubit state, which is always represented as this psi, could be a zero ket, it could be a 1 ket, or it could be a superposition of the 2. So this is a way of writing it out. We don't want to think of this, so I guess I should have drawn my own X over this, but what we don't want is to say, oh, we have a 50% chance of being in the 0 state and a 50% chance of being in the 1 state, therefore this is what we get. These are not probabilities. They are probability amplitudes. And the requirement for a probability amplitude is that the total sum of the probability amplitudes, is that the sum of all of the amplitudes squared. Oh no, I'm just gonna keep getting messages now. I wish that this was not being recorded, but I don't know a way to disable it. Actually, I'll put myself, I can't go into airplane mode because I'm on Zoom. Okay, whatever, it's fine. This will always give us 1. So if you look here, if we took the sum, or you can just write it out, actually. Write it out as alpha squared plus beta squared. We know both these are 1/2. It's 1/2 plus 1/2 equals 1. I'm on do not disturb, but unfortunately I have my, when my iPad's open, it will just keep pinging me. I don't know how to change, is there a way to change your do not disturb options? Because I have not figured it out. I swear I'm not completely incompetent with my iPad. I'm very incompetent with it, but not as bad as I could be. Yeah, sorry, just disregard the notation, the notifications coming in. So this is how you describe a probability amplitude, and the prefactor on each of these states is always going to be your probability amplitude here. So in this case, our alpha itself is 1/√2, 0 plus 1/√2, 1. And this you could also represent, if you wanted to represent it as a vector instead, you could take this as 1, 1 here, √2. Yeah, maybe I should, let me see if I can, I guess I can't pause settings. Let me see if I can easily go to my settings and just turn off notifications. Do not disturb. Always. Okay, cool, we fixed it. Great. Now, yeah, so this is another way you can represent this, this result. And I think I'm gonna say the wrong value. This might be a minus state. I always forget which way is plus and which way is minus, but there are other ket states that you can represent as different bases. So you have like a plus minus basis that you often deal with. And I'm almost definitely confused the two. But yeah, so I'm not gonna try to write that out, but you can also describe it just like this. So yeah, this is kind of a discussion of what we already went over, where we care about the probability values. Oh no, you guys are, yeah, you're totally right. It would make perfect sense. This should be a plus state. And this should be a minus state. I don't know why I don't have my life together so much. This should be a minus, not a plus. So thank you, Eric. So we care about our probabilities, where we care about the square of our probability amplitudes, because that will give us our probability, and we know that our probability must always sum to 1. So this is the same kind of vector multiplication. So if we took this was 1, 1 maybe, we could take this as 0, 1 times 0, 1, and that would just give us our 1 out. And all of our states will end up with the same normalization. So if we did the plus state, we noted, or we tried to note before, that would give us 1, 1. I guess I'm gonna put my normalization at the end because I always forget about it and then just put it at the end. This is 1/2 because that's the square of 1 over root 2. And that just gives us our 1 plus 1 over 2 equals 1. And so this all works out. We can, obviously, with our minus state, we can have negative probability amplitudes, but because we square them, they end up becoming functionally positive, and then we end up with everything still being normalized all correctly, as you would expect. Okay, so here is a representative example of a non-equal superposition state. So we know our probability is 4/5 that we're in the 0 state. So we know that our alpha squared is 4/5. Same for our 1 state, it's 1/5. Our beta squared is 1/5. So to get our actual psi, we know that we need to have the square root of each of these results. So that's the square root of 4/5 0 plus the square root of 1/5 1. This is the result of our actual state. We just have to remember to always have this extra square root term here. So here's our important takeaways for this. I know we're not even quite 15 minutes over, so it's not too terrible. Our random variable is our descriptor of all the possible outcomes of whatever we're trying to do. We always like to put these as numbers, just because that allows us to do mathematics on these states and represent these states numerically, which gives us a lot of extra power. Our probability mass function is a function that describes what the probabilities of each of these random variable, of what this random variable will give you. So each of the possible outcomes has a certain probability, and this function describes those. If we have independent events, again, we only discuss independent events. There are such a thing as dependent events, like if I left the house before 9 a.m., what is the likelihood I'm wearing shoes? Maybe it's lower than if you left it after 9 a.m. I don't know. There are dependent events that can happen like that, but we didn't really discuss them today. I don't know if we're going to, we might discuss them later on. And then we want to note that I've kind of been doing it the whole time, but our bra, which is this guy, gives us a row vector. Our ket, which is this guy, gives us column vector. I don't know if that was super clear. I guess I'll put an X here to make this a little clearer. And then we want to note that all of our qubit states are always the amplitudes, not the probabilities themselves. So these probability amplitudes, I guess, kind of just describe the distribution of our quantum state in space and energy, whatever metric we're using. And these amplitudes are what are most convenient to use for this mathematics. So if you're familiar with the Schrodinger equation, we're using these quantum states, which are probability amplitudes, to describe it. So that's just H psi is E. psi. All of our math works with these probability amplitudes, not the probabilities themselves. Yeah, so with that, I'll open it for questions and we'll do post-lab Zoom feedback if you guys have, hopefully you learned something. I know I went a bit over, but yeah, Kim, if you wouldn't mind doing that up, and I'll go over any questions. Especially we didn't zoom through the last bit, but we did go a little bit faster than maybe we would have otherwise. Great. Ooh. So I've gotten a question from Carlos with the histogram of a quantum dice. I mean, if you're just looking at the probabilities, you would treat, I guess, if you tried to make a little plot here, where like here is 0, here is 1, the height of each of these, I'll make them different heights so it's more general. This height would be your alpha squared, and this height, oh, I shouldn't have done it in red. I was told that some people use red screens to view, and so cannot view red annotations. That would be our beta squared. So it's pretty much the same thing. It's just more fun notation overall. Okay, so I've gotten a question about the expectation and variance of joint events. That's a little bit out of scope. I'd recommend looking it up. But yeah, so there's the way that you'll often see it written, if you're curious, is the probability of event X given event Y. And that depends on the functions of both of these variables. Maybe, I guess it makes more sense to describe it as a continuous variable, but I guess it could easily be discrete, where maybe you have maybe the probability of like X of like some particular outcome is actually, I don't know what the best way to describe it is, but it's a little bit more complicated, is kind of what I'm getting at. It's a little bit outside of the scope, but we could describe, yeah, I guess there's a, yes, then there's a closed form for it, but I guess the intuitive approach is a little bit less clear. So I've got a question from James: if scientists purposely try to lower the variance to get the desired result? And yes, we do exactly that. So a lot of times you'll think of things in terms of conjugate variables. So we haven't really covered what things might exist, but conjugate variables include position, which is X, let me put this out, and P, which is momentum, and energy, and time. Wow, I am so inconsistent with my notation right now. So maybe we want to, I'll write this a little bit more clearly. Maybe we want to measure some specific position. Well, whatever we're trying to measure, we're going to disregard what its momentum is pretty much entirely, except that there could be a lot of variance of its momentum, but we can get a very precise value for its position if we do that. And there's always going to be some fluctuations in any of these states. So if we took a value like for our energy, if we want to know exactly what the value of our energy level is, well, there's going to be fluctuations of that energy level. But if we just measure it over a long period of time, we can get a pretty clear estimate for the average value of that. And so even if the variance is pretty large, we can narrow down what the value is more accurately. So that's something that people do a lot, actually. Okay. Don't have any more questions right now, but if anyone else, okay, so I've gotten a question from Rohan about what these states are. Oh yeah, I didn't actually note these in the block sphere. If we take our 0 state to be up here, our 1 state to be down here, let's do the equator. Maybe our plus state is over here, and our minus state is over here. I forget which axis they're on, actually. I think that's right. No, it's not right. We want to go around X halfway. So I think we should be on, I mean, it depends which axis you define as which is not always consistent, but if we could define this as our plus state, if my pen will continue to work, and this as our minus state. The whole idea is just that they're superposition states. This is our x-axis here. This is our y-axis. We just want to note some locations of superposition states. It's just to show that you can generalize a lot of these formulas a lot more. Because when we're just dealing with these really simple 0, 1 states, it's very intuitive, I think, if you're used to thinking in a Cartesian coordinate system, where you could easily say, oh, like the 0 state is along X and the 1 state is along Y. It's all very intuitive. But now a lot of times you work in the plus minus basis, where instead you're dealing with everything is a superposition of your plus and minus states. So you could equally describe this state as alpha plus beta minus. And there's times where that might be more useful. It's just a different basis to work with. But yeah, okay, so now we're quite over time. So I think I'm going to have to call it for today, but feel free to ask all of your questions on Piazza, especially if there's a more complicated question. I am willing to give more in-depth answers on things. But yeah, it's I don't want to go too much more over today. Let me try to get my Zoom back. Okay, great. But yeah, thank you all so much for coming and attending, even though we've gone quite a lot over time. Next time I will definitely debug this in between and ensure that there are not future issues. I'll have both set up, I guess, just in case. Okay, thank you everyone. Bye.